In 1831, 3 months after his first exposure to Cambrian geology, young Charles Darwin embarked on an expedition that would influence the development of his theory of evolution. As naturalist aboard the HMS Beagle, Darwin sailed to the Galapagos Islands, 600 miles off the coast of Ecuador. For 5 weeks, Darwin explored this remote island chain, home to an extraordinary assembly of animals. Here, the idea for his tree of life was planted. According to Darwin, as one form of life morphed into another, new species arose. And as they gradually branched apart, larger differences in form emerged. Eventually, evolution produced an even greater level of disparity, the distinct body plans of new phyla.
Phyla are abstract categories that bring together basic features that unite large groups of animals. So you can think about a phylum as a group of organisms that all share a basic architecture.
Based on the body plan of the animal, we divide animals into these major groups. There's vertebrates, the backbone and soft bodies outside the bone structure. There's arthropods, which have a hard skeleton on the outside and a soft body on the inside. These are the insects and the crabs. There's the echinoderms, which are the sea urchins and starfish.
Sea stars are different from jellyfish, different from worms, and different from crabs and lobsters. So each group has their unique features to make them very different from the next group.
The stability of these forms in the animals that exemplify the distinct phyla contradict Darwin's vision of an interconnected tree of life.
The phyla don't blend imperceptibly one into another. Arthropods, for example, didn't evolve from chordates. Mollusks aren't the offspring of sponges. Instead, a phylum is, in effect, as different as it can be from another phylum. So, how did these differences arise? If one reads The Origin of Species, it's clear that Darwin's caught in a bind.
Natura non facit saltum. That was Darwin's famous Latin phrase, which means, nature takes no sudden leaps. In fact, Darwin went on to say that if you found evidence of saltation, of sudden appearance in the fossil record, that would be something like evidence of special creation.
One of the most striking examples of a sudden leap in nature is evident in the number and stability of new animal body plans that first appeared during the Cambrian explosion.
One of the other remarkable things about the Cambrian explosion is that a huge percentage of the total number of phyla that have ever existed on Earth all appear within a very narrow window of time.
It's a defensible statement that most of the major animal body plans are present in the Cambrian explosion. That's where they first appear. Imagine a graph, if you will, of the appearance over time of phyla. In Darwin's picture, you'd have 1, then 2, then 4 perhaps, then 8, a gradually increasing curve of the number of phyla growing over time.
What you actually have in the fossil record is a sudden spike in the number of phyla that appear during the Cambrian, and then a few that trickle in across the rest of geologic time. This kind of discontinuity is radically at odds with the Darwinian picture of the history of life.
The pattern we see is the major body plans present at the beginning, and that the organisms that we know today fall into one or another of those major body plans. They don't gradually increase over time.
The sudden appearance of animal body plans deepens the Cambrian mystery in another way. The Darwinian model predicts that as new biological forms evolved, simple to complex, they developed gradually from the smallest differences in classification to the largest. or from the bottom up.
Darwin's idea was that given enough time, evolution would lead to new species, new families, orders, and eventually phyla. And only after millions and millions of generations do you end up with, the several dozen phyla that we see around us nowadays. That would be the bottom-up pattern predicted by Darwin's theory.
Now, the other picture is top-down. The top-down picture says the primary differences are original. They're there right at the start. When you find mollusks in the fossil record, or the arthropods, boom, there they are, with the major differences present right at the beginning. So the upper level architecture is top-down, present right there.
This top-down pattern of biological development can be compared to the development of human technology.
If you look at any major invention, like the automobile, for example, the basic body design is set in place from the very beginning. You've got 4 wheels, a chassis, a drive shaft, 2 axles. There are certain basic features of all automobiles that have persisted since Ford and Benz got the whole thing going over a century ago.
In the decades that followed the introduction of the automobile's basic framework, designers and engineers have created thousands of variations on the original theme. But regardless of differences in size, color, and chassis design, the foundational body plan remains consistent to its original form.
And an interesting thing about the fossil record is that there's a similar top-down pattern evident in the history of life. The basic body plan of the arthropod phylum has a segmented torso, jointed legs, and an exoskeleton, all of which arose suddenly at the beginning of the Cambrian explosion. And today we still see the continuity of this original plan, this foundational idea, in over 1 million species of animals.
This top-down pattern looks nothing like the predictions of Darwin's theory.
Darwin's theory is that there's a tree of life where you have one organism diverging into many other organisms and big differences appearing at the top. What we really see is from here up. This does not exist in the fossil record. If I were using a botanical illustration, it would be a lawn with separate blades of grass sprouting independently of each other. And those would be the phyla. Now within each phylum, there is subsequent diversification, but even there, I don't see the branches connecting that would make them a tree of life.
Darwin was caught in the grip of a deep dilemma. The fossil record showed him one thing, his theory told him something else. He comes to an impasse at this point, and he says, if this pattern holds, it is a genuine argument against my view. And I think 150 years later, we've added a great deal more detail to the picture, but I think the basic problem is still unsolved.